Okay, so today we're going to cover some vector basics. So let's say vector basics. Mainly, there's kind of four main things I want to talk about. I want to talk about how they're represented, scalar multiplication, vector addition, and vector decomposition into component vectors. So for representation, remember we said that a vector was a magnitude with a direction. And there's a couple ways we can denote this. One way, if this is our x-axis and this is our y-axis, we could, let's say we'll start our vector here at the origin. We could draw an arrow that represents our vector v. We'd have to give what angle so we know the orientation, and the length of the vector v will tell us the magnitude. So this is one way you could draw it. So we draw it with an arrow. Usually you try to line it up with either the coordinate system or some point that is significant on like a free body diagram or something like that. Another method is we could list it by its x hat and y hat components. So we could say a vector v maybe is 3x hat minus 2y hat. If we wanted to draw this vector, we could say, all right, here's our x and y. We'll start at the origin. So we have 3x hats as you go 3 units to the right, negative 2y hats as you go down 2 units. This will be where the tip of the vector stops. And you start at the origin and you would draw till you hit there. And then that would be the vector, that would be our vector v we just mentioned right here. So you can represent it in this manner, and then you will build you're able to graph it from that manner pretty easy. Another way is we could say, use this kind of array notation. Vector v is maybe it's 5 and 2, and it's understood that this has basis x hat, y hat. So we could write this vector v 5 and 2. Another way we could write that vector v would be vector v is 5x hat plus 2y hat. And then if we wanted to draw it, this one would be 5 units to the right, because that's the x hat amount, or it's the top coordinate amount. And then the y value would be the 2 units, and we would have a vector that looks kind of like this. So there's also another way of, you can do these in terms of rows, but we'll just stop there with the representations. And most physics classes and stuff are going to draw them this way, represent them like that, and give you a lot of the x hat, y hat. And occasionally you'll see this, but that would be our basic vector representation. So now that we got something with that, we want to talk about scalar multiplication. If you remember from the little video we watched, scalar is just a magnitude, but it has no direction. So if we had a vector v that is equal to, let's say, 2x hat plus a single y hat, which we could write as just y hat. There's really a 1 here, but we don't write it. And most of the time when we put this in physics books, multiplication by 1 doesn't do anything, so a lot of times we'll just leave it like that. So if we wanted to draw that vector v over here, let's say that vector v would be 2 x values, 1 y value, and it would generate an arrow like this. So this right here is our vector v. Now, let's see here. If we wanted to do, say, 2 times v, let's use different color. So let's say we want to do 2 times the vector v. All you do is you multiply all the components by 2. So 2 times 2 is 4, so this would be 4x hat, plus, if there's a single y hat, 1 times 2 would be 2y hat. And if we draw that vector, let's make our x tick marks the same distance and the y tick marks the same. This now goes 4 units to the right and up 2 units. And this would be our vector 2v. And kind of comparing it with vector v, basically what happens is this vector here is just twice as long. So this vector here is twice as long as the original vector it came from, which makes sense because multiplying by 2, we kind of think of that as doubling. So we say, all right, well, the vector 2v is twice as long as the original vector. If we did 3v, that would be 3 times as long as this vector. But the orientation, the direction, is still the same. So when you do scalar multiplication, it doesn't change the direction of the vector. So next thing we want to do is vector addition. So we'll do this with the x hat, y hat stuff first, and then we'll look at doing it with drawing it graphically and kind of see how that goes. So let's say we have vector A, and vector A equals negative 2x hat plus, let's say, 3y hat, I guess. And let's say vector B is 3x hat, say minus a y hat, so minus a single y hat. If we want to do vector A plus vector B, we can write out A's vector in terms of its x hat, y hat components, and we can add that to B's vector in terms of its x hat and y hat components. We can drop the parentheses because there's nothing here to distribute and there's nothing there to distribute, so we get negative 2x hat plus 3y hat plus 3x hat minus a y hat. And now we just have to go through and add x hat stuff together and add y hat stuff together. So negative 2x hat, we add that to 3x hats. There's negative 2x hats here plus 3x hats there. We end up with a single x hat. And I'm not going to write the one out front for the same reason we did earlier. Then if we got 3 y hats here and we take away 1 y hat, 3 y hats minus 1 y hat says you have 2 y hats left. So if we draw the graph of this, we get 1 x hat, 2 y hats, and we end up with this vector. Draw it slightly better. We end up with our vector A plus B. So vector A plus vector B is this little diagonal vector here. Let's look at starting from these two without going through and knowing that we're going to add them that way. Let's look at doing this by the tip to tail method of vector addition. So this is adding them kind of graphically. Most of the time in engineering and physics, you need to know the actual numbers, so the graphical drawing can be helpful, but most of the time you need to go through and actually calculate it out to figure out what your actual numbers are. So the tip to tail method. We draw the vector A first, so this would be 2 units to the left and up 3 units. So it's 2 units to the left, and it's up 1, 2, 3 units. That is our vector A. And then, so this from the tip of A, we're going to draw vector B. So vector B goes 3 units to the right. So it's 1 unit, 2 units, 3 units to the right, and it comes down 1 unit. So vector A left off there, vector B kind of traces backwards. And then to get vector A plus B, if you start where vector A started and you draw the vector, draw this with a different color. So you start where vector A started and you draw this to where vector B's tip left off, that will be vector A plus vector B. And we see that this is up, this vector here, it's up 2, so it's 2 y hat, and it's right 1, so it's 1x hat. So it's up 2, right 1. This one down here is up 2, right 1. We can see it gets us to the same place. So with vector addition, that would be called the tip-to-tail method to add the vectors graphically. Okay, moving along. Last thing we want to do is decompose a vector into its component vectors. So we'll say decompose vector into component vectors. So suppose we have a vector here that is 5 units long. Give it the name v, I guess. So this is vector v. Vector v is 5 units long, and vector v is making a 30-degree angle with the x-axis, we could say. So I'm not going to draw the whole coordinate system in, but suppose we have a vector that's it's oriented like this. So what we want to do is this vector has an x component, which draw the x component in orange. So there is an x component to this vector. I guess we call it vx. So the vector vx is the x component vector. And there is a y component to this vector. Let's use a greenish color. And that y component, we can call that vector vy. So we got vector v is the original diagonal one. Vector vx is the x component vector. Vector vy is the y component vector. Since this is horizontal and this is vertical, these do make a right angle with each other, so this makes a right triangle. So what we want to do is we want to figure out what are the actual, what's the actual x value here, so what is that distance? So what is the x value of this distance, and what's the y value of that distance there? In a lot of problems that we're going to deal with, especially in like statics, things like that, you have diagonal stuff and they need to be decomposed into their component vectors. So if you guys note, hey, that's a right triangle, you may remember from, I think it was Principles of Technology, we had SOHCAHTOA, be from you guys' geometry class, or pre-calc, I guess. I think you do it in both. So we know we got a 5 here, we know we got a 30 degrees here, and what we need to do is basically figure out our x component and our y component. So I'm going to label all the sides of this thing. So I'm going to use a different color to label sides. I guess we'll use, I don't know, yellow. This right here is the longest side, so it's the hypotenuse. This is the side that helps to form the angle, so it's next to the angle, so this is our adjacent side. And this angle opposite the triangle from the angle is the side that we call our opposite side. If you guys remember, the position of the angle that you're given determines the adjacent and the opposite. Hypotenuse is always the longest, but the one across the triangle from the angle is opposite, and the one that helps to form the angle is adjacent. So we have x and we have 5. So we have x and a 5. So x is adjacent, 5 is hypotenuse, so I need the one with a and h to form my x value. A and h is CAH, so we're going to go for the x, we're going to use CAH. The equation we get is C stands for cosine. Our angle is 30 degrees. So we get cosine of 30 degrees equals the adjacent side. Adjacent is the x value here. It's the length of the vector vx, so that'll be our x value that we're looking for. And h is the hypotenuse, which is 5. So we multiply the 5 across to solve this for x, which is the length of the vector vx, and we get 5 times cosine of 30 will be our x component vector, or that'll be the length of our x component vector. So I guess let's pull up Desmos real quick and see what that value actually is. Okay, let's see here. So we need 5 times cosine of 30. Okay, I think they're doing this in radians. Is that right? Let me see here. Well, let me check it in my calculator because there's two modes of angle measurements. One's degree and one's radians. So I'm trying to remember. I don't remember which one Desmos uses. I know which one my little graphing calculator I have on my phone is. So I'll put this in degrees, and we're going to do 5 times cosine of 30. And my phone's giving me back 4.33, which is what I would expect. So this right here, let's see, if we want to convert from degrees to radians, let's see here. So we're supposed to get like 4.33012. So let's see here. 30 is in degrees. I think I can multiply by pi and divide by 180. I think that does it. Yeah, so this right here is a degree reading. Desmos, I guess, has this set to radian. So I need to multiply by pi over 180 to convert the degrees to the radians. And then I get the number I'm expected to get, 4.33 back. For you all, for using Desmos, just pi over 180 will convert degrees to radians, and then 180 multiplying by 180 over pi converts radians back to degrees. So we're going to just say, all right, this is about equal to our x length. It's about equal to 4.33 units. I didn't give units here, so we don't really know what those units are. But we do know the x down here is 4.33. So if we want to write the vector Vx equals 4.33 in the x hat direction. So there's our component vector Vx. A lot of times in engineering, or physics, a lot of times we're working with just the lengths of these things, so we don't necessarily always write it kind of like this. Sometimes once we know that length is 4.33, we can just go directly to an equation and get our information we want from that. All right, so Vy. Vy is opposite, and we got a hypotenuse, so it's OH. So we're going to look at SOH. So that's sine of our 30 equals our unknown y value, because O is opposite, so that's unknown y value. And then we divide that by the hypotenuse 5, multiply that across, we get 5 sine of 30 equals our y value. So if 5 sine of 30 is our y value, let's go back to Desmos and we'll put it in there. So we get 5 sine of 30, and I need to convert this over to degrees, so it'd be pi divided by 180. Close our parenthesis, close our parenthesis, and that equals 2. So we get that this is our y value, it's about equal to 2. So the y length here is 2, and that tells me that Vy will equal 2y hat. So we decompose the x value, this diagonal vector, down to its horizontal and its vertical component. And when we do some of these free body diagram problems and some of these statics problems, we'll see that being a common theme that we do. So stop there.